Have you ever looked up at the night sky and wondered where it all began? Not just the stars or the galaxies, but the very light that lets us see them. The story starts in a place completely alien to us, a universe without light. Imagine for a moment, a time before the first star flickered into existence, before galaxies began their slow cosmic dance, before even the faintest glimmer of light, there was only darkness. But this wasn't an empty void. It was the afterglow of creation itself, a universe just born, incredibly hot and expanding rapidly, but utterly blind. For the first 380,000 years after the Big Bang, the cosmos was a strange place. It was filled with a superheated, glowing fog of particles, a dense plasma of protons and electrons. Light was there, photons were everywhere, but they couldn't travel. They were trapped, bouncing endlessly off free electrons like a pinball in a chaotic machine. The universe was brilliant on the inside, a blazing inferno, but from the outside, it was opaque. No information, no images could escape. It was a prison of light, and something incredible happened. As the universe expanded, it cooled. It cooled just enough for a monumental shift to occur. Protons and electrons, which had been zipping around freely, finally slowed down enough to connect. They formed the first stable, neutral atoms, mostly hydrogen and helium. This event, known as recombination, was one of the most important moments in cosmic history. It was a quiet, invisible transition, but its consequences were profound. Suddenly, the fog lifted. With electrons now bound to atomic nuclei, the photons were no longer scattered. For the very first time, light was set free. Imagine a single, universe-spanning flash. In an instant, the cosmos became transparent. This first burst of liberated light, released everywhere at once, is what we now detect as the cosmic microwave background, or the CMB. It's the oldest light in the universe, an echo of that first dawn, still washing over us from every direction in the sky. It's a baby picture of our universe, just 380,000 years old. This moment marked the beginning of the Dark Ages. It sounds like a step back, but it was actually the necessary next step. The universe was now dark and transparent, filled with vast clouds of neutral hydrogen and helium gas. For millions of years, gravity was the only force at work, patiently pulling these gas clouds together. Slowly, silently, clumps began to form. In the densest regions of these clouds, pressure and temperature started to climb. Over hundreds of millions of years, these cores grew hotter and hotter until they reached a critical point. A point where atoms, crushed under immense gravitational force, began to fuse. And then light. Part 2. The first stars ignited. These weren't like our sun. They were cosmic monsters, hundreds of times more massive, burning millions of times brighter, and living incredibly short, violent lives. They were forged from pure hydrogen and helium, the raw materials of the early cosmos. When these first stars blazed to life, they flooded the universe with a new kind of light-intense, high-energy ultraviolet radiation. This light was so powerful that it ripped electrons away from the neutral atoms that had filled the universe. A process called reionization. The universe, once a neutral fog, became an ionized plasma again, but this time, it was different. It was vast and mostly empty, punctuated by the brilliant island cities of stars and galaxies. The darkness had truly learned to shine. Every photon that reaches your eye carries a piece of this history. Light from our own sun tells a story that began 8 minutes ago. Light from the nearest star, Proxima Centauri, carries a memory from 4 years in the past. And when we look at the Andromeda Galaxy, we are seeing light that began its journey 2.5 million years ago, long before modern humans walked the Earth. With telescopes like the Hubble and the James Webb, we can look even further back, capturing light from the universe's infancy. Seeing galaxies as they were just a few 100 million years after the Big Bang, we are, in a very real sense, time travelers. Every photon is a messenger from a bygone era, carrying the story of its origin of stellar nurseries, cataclysmic supernova, and colliding galaxies. From a hot, opaque fog to a vast, transparent darkness, and finally to a cosmos illuminated by trillions of stars. The story of light is the story of the universe itself. It's the story of how nothingness learned to see, how darkness gave birth to brilliance. So the next time you gaze at the stars, remember you're not just seeing distant points of light. You're witnessing the final chapter of a journey that began nearly 14 billion years ago, in the first flash of a universe learning to shine. To understand the origin of light, we have to journey back to a time when the very concept of seeing had no meaning, when the universe itself was blind. Imagine winding the clock back 13.8 billion years. The Big Bang erupts, giving birth to space, time, energy, and all matter. But what followed wasn't a sudden flash of brilliance. It was sheer, unimaginable chaos. For the first 380,000 years, the universe was a seething, violent ocean of plasma. Think of it as a superdense, scorching hot soup of protons, electrons, and photons, all locked in a frenzied dance. Light certainly existed in this primordial soup, but it couldn't go anywhere. Every single photon, every particle of light was constantly colliding with charged matter. It was absorbed, spat back out, and scattered in every direction. The universe was luminous on the inside, but completely opaque to itself, much like the interior of a star. Physicists call this period the photon epoch. During this time, radiation, not matter, ruled the cosmos. Temperatures soared to nearly 3,000 Kelvin, so hot that atoms simply couldn't form. Anytime a proton tried to capture an electron, a high-energy photon would immediately blast them apart again. This was light, yes, but it was imprisoned light. The cosmos glowed, but nothing could escape that glow. This was the opaque universe, a cosmos still too hot and dense for light to travel freely, but all the while, a silent, powerful force was at work. Expansion. As the fabric of space stretched, the universe began to cool. And that cooling was about to trigger one of the most transformative moments in all of cosmic history. Around 380,000 years after the Big Bang, the universe finally cooled below that critical 3,000 Kelvin mark. This was the moment everything changed. It became cool enough for protons and electrons to finally come together and form the very first stable neutral hydrogen atoms. This event is known as recombination, a bit of a misnomer, since it was the first asterisk time they ever combined, but the name has stuck. And with that combination, the universe went from opaque to transparent almost instantly. Right. It was a cosmic phase transition, like a dense fog suddenly clearing. With electrons now bound into atoms, they no longer scattered the photons. For the very first time in history, light could travel freely, unimpeded, across the vastness of space. Those first liberated photons have been traveling ever since. Stretched by the continuous expansion of the universe over billions of years, they've cooled down into faint microwaves that still fill every corner of the cosmos today. We call this the cosmic microwave background, or the CMB. It is, quite literally, the oldest light in existence. When we look at this map of the CMB, what we're seeing is not the birth of light itself, but the moment light was finally set free. It's a baby picture of the universe, captured the instant its blinding fog thinned, and the cosmos took its first breath of clarity. Paradoxically, the liberation of light also marked the beginning of a profound darkness. As those ancient photons streamed outward into the void, the universe continued to expand and cool. No new light was being created. All that remained was the faint, fading afterglow of the CMB. This period is known as the Cosmic Dark Ages, and it lasted for hundreds of millions of years. During this long dark era, matter wasn't idle. Pulled by the relentless force of gravity, it began to clump together, forming the invisible seeds of future galaxies and the vast scaffolding of the cosmic web. But there were no stars, no galaxies, no new sources of light to illuminate the scene. Space was filled only with vast clouds of neutral hydrogen gas and the fading echo of the Big Bang. The universe was transparent now, but it was an empty, dark transparency. Darkness had learned to see, but the universe had not yet learned how to shine again. But here's the beautiful part. Every single photon that was released back then is a time traveler. When our instruments detect the cosmic microwave background, we are looking directly at the universe as it was just 380,000 years after its birth. It's a snapshot frozen in time, a postcard from the dawn of everything. This ancient light is a treasure trove of information. tells us about the universe's density, its age, its composition, and even reveals the tiny quantum fluctuations that, over eons, would grow into the magnificent galaxies and stars we see today. In this sense, light is so much more than just illumination. It is the memory of the universe, the ultimate cosmic archive, recording every transformation from the first atoms right up to us. Long before life evolved eyes to see, light had already become the storyteller of creation. But the universe was not done learning how to shine. In the cold, dark oceans of hydrogen gas, gravity continued its patient work, pulling matter into ever denser clumps. And out of that profound darkness, the first true lights were about to ignite. This is the story of how the universe, once blind, once dark, would learn to create the brilliance that defines it today. The birth of the first stars, the colossal population, 3 giants, was about to transform the cosmos forever, ending the Dark Ages and setting the stage for everything that followed. For hundreds of millions of years after the Big Bang, the universe was dark. Yes, it was transparent, but almost entirely invisible. The light from the initial creation had faded into what we now call the cosmic microwave background, and no new light had yet been born. This was the cosmic Dark Aeon era, when gravity, quietly and patiently, began to sculpt the next act of creation. Inside that invisible fog of hydrogen and helium, tiny fluctuations, regionally seeded by quantum ripples in the early universe, grew denser and denser over immense spans of time. Matter gathered, cooled, and condensed. These clumps were the first gravitational wells, the cosmic cradles where the very first stars would be born. Imagine the scene, a vast, silent expanse. No galaxies, no color, only a faint, formless fog. But then, deep in the void, a ripple of gravity begins to pull, drawing matter together, setting the stage for the first dawn. When enough gas collected under its own gravity, something incredible happened. Temperatures at the core of these massive clouds skyrocketed past 10 million degrees. At that precise moment, the impossible became reality. Hydrogen atoms began to fuse into helium. And with that reaction, light returned to the universe. These were the population 3 stars, the very first generation of stellar beacons. And they were nothing like the stars we see in our night sky today. Composed purely of hydrogen and helium untouched by any heavier elements, they were unimaginably enormous, incredibly short-lived, and blindingly bright. Some of these titans were over 300 times the mass of our own sun. They burned through their fuel in just a few million years before, collapsing into black holes or exploding as titanic supernova. Each of these early stars was a factory, a cosmic forge creating light and matter. They forged the universe's first heavy elements, the first traces of carbon, oxygen, and iron. And when they died, they scattered these precious new ingredients throughout space. Their powerful radiation also reionized the surrounding hydrogen gas, transforming the once dark neutral universe into a glowing sea of energy. This monumental event, known as the Epoch of Reionization, marked the definitive end of cosmic darkness and the true beginning of starlight. As more and more of these brilliant stars ignited, gravity began to pull them together into families, forming the first proto-galaxies. These were the ancient ancestors of our Milky Way, of Andromeda, and of the billions of other galaxies that populate the cosmos today. Light, once confined to scattered lonely points in a dark sea, now began to flow between these emerging clusters and galaxies. For the very first time, the universe began to structure a grand cosmic web woven from filaments of gas, dust, and starlight. We call this era the Cosmic Dawn. It's a period stretching from about 100 million to 1 billion years after the Big Bang, a time when the first stars and galaxies fundamentally transformed the entire universe. Every single speck of light you see in the night sky today is a direct descendant of those primordial suns. They were the universe's first storytellers, illuminating space, not just with photons, but with the chemical seeds for everything that would eventually follow. But light does more than just reveal. It actively creates structure. The intense ultraviolet radiation pouring from these early stars stripped electrons from nearby atoms, ionizing the universe's gas once again. This process dramatically changed how matter could cool, how subsequent galaxies could form, and even how the next generations of stars could be born. In a very real sense, light became an architect of the cosmos. It began shaping the evolution of the universe just as powerfully as gravity itself. Without that initial radiation, without those first cosmic fires, the universe might have remained static, a cold, unchanging fog of hydrogen forever. Light wasn't just illumination. It was transformation. But this incredible brilliance came at a cost. The very stars that ended the cosmic darkness also burned themselves out with astonishing speed. After only a few million years, a mere blink of an eye on a cosmic timescale, they exploded as supernova or collapsed into the first black holes. These deaths were incredibly violent, but they were also profound acts of creation. Each explosion scattered those newly forged, heavier elements, the metals, as astronomers call the macros, vast regions of interstellar space. From this cosmic debris, new generations of stars would form. These new stars were richer in their chemical composition, generally smaller in size and capable of living much, much longer lives. And among them, billions of years later, our own sun would be born, a distant descendant of those ancient, fiery giants. Think about this. Every atom in your body, the carbon, the calcium, the oxygen, was once part of the ashes of those first stars. You are, quite literally, made of the light that once ended the universe's darkness. As light spread across the cosmos, it revealed something extraordinary. The universe, in a way, had become self-aware. For the first time, it could be observed not by eyes or minds, which didn't exist yet, but by the very photons traveling across it. Each ray of light was like a message, carrying information, saying, "This is what I have seen. This is where I have been." Through light, the universe began to build a memory of itself, and in time, life would evolve with the ability to read that memory. But the story of light doesn't end with its birth. It evolves. It gathers. It bends. It merges, as galaxies form and grow into the magnificent structures we see today. We think of the universe as being full of light, right? Stars, galaxies, nebulae, ... It's a cosmic fireworks show. But have you ever wondered when that show actually started? When did the very first true asterisk light appear? The answer seems simple. I mean, light has existed since the Big Bang, or at least since about 380,000 years after it, when the first photons broke free. But that light, the cosmic microwave background, wasn't the light of stars. It was more like the universe's baby picture, a uniform glow from a time before structure, before stories. It was light without a storyteller. The real mystery begins, asterisk after asterisk, that, in the long, dark centuries that followed, the universe went silent and waited for its first fires to be born. Welcome to the cosmic dark ages. This was the time between that initial flash and the birth of the first stars. The universe was transparent, sure, but it was utterly, profoundly black. The photons from the Big Bang still zipped around, but the expansion of space had stretched them out so much that they were no longer visible light. They couldn't illuminate anything. The cosmos was filled with a thick, neutral hydrogen gas that acted like a universal fog, absorbing and scattering almost every trace of ultraviolet light. So even if a lone, brave star had somehow ignited early, its light would have been trapped, unable to escape. It's one of the great paradoxes of cosmology. Light existed, but the universe was still blind. So when did the first true light, the light that could finally travel freely and begin to shape the cosmos, finally appear? That question has haunted astronomers for decades. The problem is, we can't see those first stars directly. Their light has traveled for over 13 billion years to reach us, and in that time, the expanding universe has stretched it or redshifted it, far beyond the visible spectrum into the infrared. Until very recently, even our most powerful telescopes could only see the faint afterglow of their influence, the fingerprints they left on the cosmic gas, or the chemical traces they seeded in the void. We could estimate when it probably happened, somewhere between 200 and 400 million years after the Big Bang, but we couldn't see how. It's like finding footprints on a beach, but having no idea what creature made them. This period is the universe's first great missing chapter, a time when the laws of physics played out unseen, and light quietly fought its long battle against the darkness. For decades, that's where the story stalled. Scientists could only run simulations, and imagine what that cosmic dawn looked like. But in 2022, something extraordinary happened. Humanity's most powerful window into the early universe opened its golden eyes, the James Webb Space Telescope. Webb is a masterpiece of engineering, specifically designed to see in infrared light the stretched out, ancient remnants of the very first photons ever produced by stars and galaxies. And almost immediately, it delivered a revelation. Within just a few months of operation, JWST spotted galaxies so ancient, they were already shining just 300 million years after the Big Bang. This was earlier, and they were brighter than anyone predicted. This discovery sent shockwaves through the world of cosmology. If fully formed galaxies were shining this early, it means the process of star formation must have kicked off much, much sooner than we ever thought. It seems that light began its triumphant return almost as soon as the darkness fell. But these early bright galaxies also raise a profound new question. How could so much structure form so quickly? How did the first stars manage to ignite, group together into galaxies, and burn away the cosmic fog in just a few 100 million years? Our models are struggling to keep up. Some astronomers now suspect that the very first stars, those legendary population 3 giants, must have been even more massive and burned even more efficiently than our theories assumed. Others wonder if more exotic physics was at play. Maybe dark matter played a bigger role in pulling things together, or perhaps quantum effects in the primordial soup created dense pockets of matter faster than we expected. Whatever the cause, one thing is crystal clear. Our picture of the cosmic dawn is far from complete. We are watching the first pages of the universe's story being written. We're still trying to understand how light finally won its epic battle with darkness. But here's a beautiful thought. Even before the first star flickered into existence, the universe already held the blueprint for light. You see, the faint ripples in the cosmic microwave background, that baby picture of the universe, weren't random. These ripples, known as baryon acoustic oscillations, were essentially the first sound waves of the cosmos. These ancient vibrations in the primordial plasma dictated where matter would eventually clump together, where galaxies would form, and ultimately, where the first stars would ignite. In a way, those ripples were the musical score, and the first light was the symphony that followed. The magnificent structure we see today, galaxies arranged in great filaments, clusters, and walls, is the visible echo of that ancient cosmic music, frozen in time. And that brings us to something even more mind-bending. Every time you look up at the night sky, you're not just looking out into space, you are looking back in time. The light from distant galaxies has traveled for billions of years to reach your eyes. Each photon is a tiny time capsule, carrying a message from a universe that no longer exists in that form. When the James Webb Telescope observes a galaxy 13 billion light-years away, it is literally seeing the universe as it was when light first began to reclaim the cosmos. Every telescope is, in truth, a time machine. Light isn't just the universe's first storyteller. It is also its only surviving witness. So, even now, scientists debate what first light truly means. Was it the first photon released in the Big Bang? The ignition of the very first star? Or was it the first ray of light that could finally travel across the entire universe unimpeded by the fog? The deeper we look, the more we realize that the first light probably wasn't a single dramatic moment at all. It was a transition, a gradual, breathtaking awakening of the cosmos from blindness to vision. And perhaps, in that slow, quiet dawn, the universe was learning to see itself for the very first time. Soon that light would go on to sculpt galaxies, feed supermassive black holes, and eventually create the conditions necessary for life itself. But before light could reach our world and spark life on Earth, it first had to learn how to shape and be shaped by the matter of the cosmos. For billions of years, light has journeyed across the universe, illuminating distant stars, galaxies, and vast clouds of cosmic dust. But eventually, that very same light would find its way to a small blue world orbiting an ordinary star. And on this world, something truly remarkable happened. Here, light became life. Every single ray of sunlight that touches your skin was born in the fiery heart of our Suna, colossal fusion furnace that turns hydrogen into helium, releasing the very energy that sustains everything we know. Our sun is a second-generation star, which means it was built from the ashes of earlier ancient supernova. So the light that feeds our Earth was literally forged in the deaths of those ancient stars. When you feel the warmth of the sun, you are feeling the recycled energy of cosmic history. Light isn't just illumination, it's our inheritance. The first organisms to truly master sunlight were microscopic. Living in ancient oceans, cyanobacteria discovered how to capture photons and transform them into chemical energy through a process called photosynthesis. This single innovation changed everything, filled our atmosphere with oxygen, created the ozone layer, and ultimately made complex life possible. Light was no longer just radiation. It became nourishment, memory, and power. Every tree, every blade of grass, every single breath of air you take is part of light's long, incredible transformation into life. If you could zoom into a plant's chloroplast, you'd see it. Photons colliding with pigments, electrons leaping, molecules rearranging. Photosynthesis is one of the universe's most beautiful and elegant equations. Sunlight leads to life, which leads to awareness. It's the exact moment when the cosmos began to use light not only to exist, but to begin to understand itself. But life didn't just absorb light, it began to see it. From the simple, light-sensitive cells of a jellyfish to the incredibly complex eyes of humans, evolution shaped vision as a fundamental tool for survival. Through eyes, the universe itself gained perception. Every creature that gazes up at the stars is performing a cosmic act transforming photons into pure knowledge. Light became the messenger of truth, and sight became the mind's window to reality. When humanity built telescopes, we extended our sight across the vastness of the cosmos, turning our eyes into instruments of cosmic awareness. Every image captured by a telescope is made of light that has traveled, sometimes for billions of years, just to meet a mind capable of asking, where did this come from? Our relationship with light is what defines civilization. The first fires our ancestors kindled turned the dangerous night into a safe haven. Oil lamps guided travelers through the darkness. And then, electricity liberated humanity from the shadows entirely. Every great revolution, industrial, scientific, digital, has been powered by light in one form or another. From the simple flame of combustion to the photon racing through a fiber optic cable. Light carries not just heat and energy, but also information. It's the language of our modern world. Data flows through glowing optical fibers, and satellites beam light between continents, connecting us all. But there is another kind of light, one that doesn't come from the sun or the stars, but from deep within us. Every thought you have, every image you conjure in your mind, is carried by electrical impulses. These are tiny sparks of energy, echoes of the same fundamental electromagnetic forces that govern the entire cosmos. The photons that once shaped galaxies now shape your perception, your emotions, and your understanding of the universe. In a way, the human brain is a nebula of its own, a seamless connection between the neuron and the cosmos. Within us, the universe's light has finally become self-aware. We are the cosmos, remembering its own fiery beginning through the language of photons. Yet, light is fragile. It can be lost, scattered, or dimmed. Our planet's light, the delicate balance between the sun, our atmosphere, and life itself, is under threat. Pollution, deforestation, and the glare of our technology risk overwhelming the natural rhythms that sustain our ecosystems and our minds. If the universe spent billions of years fighting through darkness to create this precious light, then protecting it may be our greatest cosmic duty. Light gave us life, sight, and thought. It made us into cosmic storytellers. Every dawn is a reminder that light, no matter how eternal it may seem, must be cherished, studied, and preserved. We are all children of starlight. The story of light is ultimately the story of us. From the very beginning of our time on this planet, long before we had words for atoms, space, or even time itself, we knew about light. It was the first thing we noticed about the universe. The one constant, eternal, mysterious messenger that connected the heavens above with our own eyes. We looked up at the stars, the sun, the moon, and we wondered. But the true nature of light, what it was really made of, would remain a secret for most of human history. That is, until a powerful combination of human curiosity Sheer persistence and the elegant language of mathematics finally pulled back the curtain. It all started to change in 1666. Imagine a young Isaac Newton, sitting alone in a darkened room. He's made a tiny hole in a window shutter, allowing a single thin beam of sunlight to slice through the darkness. In its path, he places a simple glass prism. What he saw next was nothing short of astonishing. The pure white light of the sun exploded into a brilliant rainbow, a full spectrum of color splashed against his wall. In that moment, Newton had a revelation. White light wasn't pure at all. It was a composite, a mixture of all the colors of the rainbow combined. For the very first time, light wasn't just a mystery. It was physics. It was a phenomenon with structure, with rules, with laws that could be studied and understood. This single discovery changed everything. It proved that light carried information, that color was a clue to the hidden mechanics of nature itself. Centuries later, this exact insight would allow scientists to read the chemical fingerprints of distant stars and decode the entire history of the universe, all from its ancient light. But Newton's discovery opened up a new, even deeper question. By the 19th century, the great debate was raging. What is light fundamentally? Is it a particle, or is it a wave? Thomas Young's famous double-slit experiment seemed to provide an answer. He showed that when light passes through to tiny slits, it creates an interference pattern on a screen behind them, alternating bands of bright and dark. This is classic wave behavior, like ripples in a pond interfering with each other. Light, it seemed, was definitely a wave. But a wave of asterisk. What asterisk? What was the medium it was waving in? No one had a clue. Then came the brilliant James Clerk Maxwell. In one of the greatest unifications in the history of science, he brought together the seemingly separate forces of electricity and magnetism into a single elegant theory, electromagnetism. His equations predicted the existence of electromagnetic waves, ripples of electric and magnetic fields that could travel through space. And when he calculated the speed of these waves, he found they traveled at the exact known speed of light. The conclusion was inescapable. Light asterisk was asterisk an electromagnetic wave. For a brief shining moment, it felt like everything finally made sense. Until, of course, it didn't, because as the 19th century gave way to the 20th, a new wave of experiments began to show something utterly baffling. Under certain conditions, light behaved not like a wave, but like a stream of tiny discrete particles like microscopic bullets. They called these particles photons. Light was a wave, and it was a particle. It was both, depending entirely on how you decided to look at it. This was the first great paradox of the quantum age, and it was the universe's way of whispering to us. Reality is far stranger than you think. The next great leap came in 1905, a miracle year for a young patent clerk named Albert Einstein. He turned his attention to a curious phenomenon called the photoelectric effect, where light hitting a metal surface could knock electrons loose. The old wave theory couldn't explain this properly. Einstein, in a stroke of genius, proposed that light wasn't a continuous wave, but was made of discrete packets of energy. He called them quanta. These quanta, or photons, acted like tiny projectiles, striking the electrons and kicking them out of the atoms. It was a radical idea, and it was this explanation. It's not his theory of relativity that would earn him the Nobel Prize. More importantly, it threw open the doors to the strange new world of quantum physics. Einstein's insight completely shattered the old comfortable boundaries between waves and particles, between energy and matter. He showed us that light was a fundamental, mysterious, dual entity. And today, that very same principle is at the heart of our modern world. It powers the solar panels on our roofs. It's what makes our digital cameras work, and it's even a cornerstone of the quest to build quantum computers. Einstein turned a simple observation about sunlight into the foundation of modern technology. If Newton split light to understand color, modern scientists split it to understand the entire cosmos. This is the science of spectroscopy. We discovered that every element in the universe, when heated, emits or absorbs light at very specific frequencies, creating a unique spectral fingerprint. Hydrogen, helium, carbon. Iron each one writes its name in the language of color. By analyzing the light from distant stars and galaxies, astronomers could finally read those cosmic fingerprints. They learned what stars are made of, how fast galaxies are moving away from us, and that the universe itself is expanding. Then, in 1965, something incredible happened. Two radio engineers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna for satellite communication, but they were plagued by a persistent, annoying hiss. They tried everything to get rid of it. They rewired the system, checked their instruments. They even cleaned out pigeon droppings from the antenna, but the hiss remained. It came from every direction, day and night. What they had stumbled upon wasn't a malfunction. It was a whisper from the dawn of time itself. It was the cosmic microwave background, the faint, cooled-down afterglow of the Big Bang. For the first time in human history, we were seeing the universe's baby picture, the very first light, set free only 380,000 years after its birth. The eternal darkness finally had a story, and we were just beginning to read it. To see deeper into that story, to look further back in time, we had to get above our own atmosphere, which blurs and distorts the light from space. We had to build telescopes beyond Earth. The Hubble Space Telescope, launched in 1990, completely transformed our view of the cosmos. It captured light that had been traveling for billions of years, revealing the universe in a clarity we had never imagined. Take a look at Hubble's famous deep field image. Every tiny speck of light in that image isn't a star. It's an entire galaxy, each containing billions of its own stars, each star a potential sun for planets that might harbor life. But we wanted to see even earlier. To do that, we needed a new kind of eye. An eye that could see in infrared light, the ancient light from the first stars and galaxies that has been stretched out by the expansion of the universe over 13 billion years. That eye is the James Webb Space Telescope, folding its magnificent golden mirrors in the cold darkness of space. Webb is a true time machine. Its very first images stunned the world, revealing galaxies that were shining just a few 100 million years after the Big Bang. It was as if we had built a time machine out of mirrors, gold, and mathematics, and finally caught a breathtaking glimpse of creation's opening act. Today, light has become our most powerful and versatile tool. It is a universal language. Use it to explore the unimaginably large, the vast cosmic web of galaxies, the violent hearts of quasars and the infinitesimally small, like individual atoms, molecules, and even the bizarre quantum vacuum itself. But it's not just for science. Light is woven into the very fabric of our civilization. It carries our phone calls and internet data through fiber optic cables. It stores our memories in photographs and our dreams in the digital cloud. In a very real sense, light has become the carrier of human consciousness itself. In our long journey to understand light, we have learned so much more than just physics. We've learned how the universe works, but also how to see it, how to measure it, and how to harness its incredible power. From Newton's simple prism to the intricate golden mirrors of the James Webb Space Telescope. Our story as a species has always been about learning to listen to the messages carried by light. It speaks to us across unfathomable distances of space and time. And every time we learn to understand it a little more deeply, we can hear the universe speaking back. This journey of light is also our journey of discovery. It's a grand dialogue between the cosmos and our own consciousness, written in photons, and finally decoded by the human mind.